Okay, so welcome back for the next and last session of this afternoon. So we have the great pleasure of welcoming Lorenzo Baldi, who is part of the POEMA project. And he will talk about new bounds on Putinar's Positivstellensatz.
Okay, thank you for the introduction, and I'm very happy to give this talk also partially in presence. So let me start. No, it's not working. Okay, let me start just briefly recalling the basics of polynomial optimization to fix the notations. So we will have our objective function f, that is a n-variate polynomial, and we will have our constraints g1, gr that defines the basic closed semi-algebraic set S, and the goal of polynomial optimization is to find f star, that is the infimum of f over S. So the first observation is to notice that f star is equal to the supremum of lambda, such that f minus lambda is a positive polynomial on S, but the convex cone of positive polynomials is intractable. Even if you truncate it in finite dimension, it is not easy to determine if a polynomial is positive or not on a basic closed semi-algebraic set S. And so the idea is to find inner tractable approximation of these positive polynomials to compute lower approximation of f star. So we will need some square polynomials that are denoted sigma squares. And then we will need the basic object of this talk, that is the truncated quadratic module at level L, denoted QL of G. That is the polynomials of the form sum of squares plus sums of SIGI, where SI are all sum of squares, and the degree of every addendum in this sum is bounded by L. So this will be the truncated quadratic module at level L, at degree L, and represent the polynomials that are generated in degree L. And okay, of course, this is a subset of the positive polynomials of S by definition. And so we can define the Laster sum of square hierarchy, that is for an integer n. L, we define f star S as L as the supremum for lambda, such that f minus lambda is in the truncated module at level 12. And this defines a hierarchy of lower approximations of f star. And the first question that we ask ourselves is that, do we have convergence as L goes to infinity? And the answer is yes, if the Archimedean condition is satisfied. And this is because of Putinar's Positivstellensatz. So we know that if the quadratic module generated by the inequalities gi is Archimedean, and f is a strictly positive polynomial on S, then f belongs to the quadratic module. So the next question, the next natural question is the following. What is the rate of convergence of the lower approximation to f star as L goes to infinity? And a related question, I would say almost the same question, is the following. If f is a strictly positive polynomial on S, then we know that f belongs to the quadratic module by Putinar's Positivstellensatz, but the question is, at which level we'll find it? To which degree we will find a representation of S? And okay, I will fix some notations that I will recall during the presentation, but it's better to fix them now. So we will have our f, that is a polynomial strictly positive on S. I will denote d or d of f, the degree of f. And then I need to introduce some measure of how close is f to have a zeroness. So for this, I need, of course, f star, that is the minimum of f on the semi-algebraic set. And I also need the norm. So I denote the norm of f as the max norm of f on the hypercube. And it will be clear later why we choose this norm. And so I define epsilon of f, that is f star divided by norm of f. And this measures how close is f to have a zero on the semi-algebraic set S. Now, some related literature. First, I want to highlight a recent result by Monique and Lucas that deals with the case of the hypercube. And in particular, it is not a version of Putinar's Positivstellensatz, but of Nutgen's Positivstellensatz. So we have the preordering and not the quadratic module. We also need to consider the products of the generators. So what they proved is that there exists a constant that depends on the number of the variables and on the degree of our f, such that if f is strictly positive on the hypercube, we know that f belongs to the preordering at level n times r, the preordering of the hypercube, when r is bigger or equal than the maximum of the first quantity, that's not so important, and the second, which is the one we are interested in. So if there is this constant, and then you can see there is norm of f divided by f star. So this is our epsilon of f, and we have a square convergence. We have this square root that makes the convergence quadratic. And here we also have an estimate of c, and I want to report also the order of this estimate because it's important also for our proof, even if maybe I will not go into the details. So this theorem is important because we will use this result of the hypercube to prove our general effective Positivstellensatz. And let me mention some other results. First, an effective version of Smoothgen Positivstellensatz by Markus Verhoefer, where it proves a general result for the effective Smoothgen Positivstellensatz. You can find in Fang and Fauzi an analysis of the convergence for the hypersphere for homogeneous polynomials. In this other work by Monique and Etienne, you can find an analysis of the upper hierarchy of sum of square densities. And finally, let me mention this paper by Christoph Kurbika and Paul Zieja, where they study a sub-cone of the quadratic module generated by the GIs and prove an equivalent effective, an equivalent version of the effective Putinar Positivstellensatz. Okay, and now let's move to the elephant in the room. That is the theorem by me and Markus. So if we have, with the same notations, the quadratic module Q Archimedean, and well, a normalization assumption, so the semi-algebraic set S included in the interior of the hypercube, then there exists a constant that depends on the description of the semi-algebraic set and, of course, in the number of the variables, such that F belongs to the quadratic module at level L when L is bigger or equal than C times the exponential of a quantity that involves, you see, our epsilon of F. So we will have exponential of epsilon of F to the power minus C. This norm is not a norm that we will use. It is another norm, but they are equivalent. It's so important to go into these details. So this is what we have up to now in the literature, and we want to improve this result in these ways. First, we want to prove a new bound that is polynomial in epsilon of F. And second, we want to have explicit exponents as much as possible. Now, let's move to the statement of the theorem. First, I need some normalization assumptions. The first one is that we assume that the ball that is in the quadratic module is the unit ball. So this also implies that the semi-algebraic set S is inside the hypercube, the unit hypercube. And second, we also need that the max norm of the GIs of the inequalities on the hypercube is bounded. These two assumptions are not so restrictive, and we can simply ensure that they hold by a change of variables and by scaling the inequalities. So we will also need another ingredient that is the Logistic inequality, and we define d of x as the distance from a point x in R to the n to the semi-algebraic set S, and then we define the algebraic distance g of x, capital G of x, as the absolute value of the minimum of G1 of x, GR of x, and 0. And this is the algebraic distance. So it's important to remark that these two functions have the same zero set. So, of course, if a point x is in S, then the distance between x and S is 0. And also for G, because if a point x is in S, then all the GI are greater or equal than 0. So this minimum will be 0. And so also G of x will be equal to 0, capital G of x. On the other hand, if x is not in S, then the distance will be strictly positive. And for G of x, what we have is that at least one of the GI will be strictly negative, and so this capital G of X will be strictly positive. And okay, so this, sorry, how can I cancel? I don't know. So this somehow the algebraic distance relates, describes somehow the complexity of the description of the same algebraic set S, and the Logistic inequality capture this complexity. This the inequality tells us that there exists a constant C and exponent L, such that for all the X in the hypercube, the distance to some power L is more or equal than a constant times the algebraic distance. So when the description will be good, then we can expect L to be equal to 1, and we'll prove it. And when the description is bad or the same algebraic set X is singular, we expect L to be big. Okay, now let's move to the theorem. If we assume that n is bigger or equal than 2, well, it's not really restrictive. It is just to simplify the exponents, and also n equal to 1 deserves a special attention. So if n is bigger or equal than 2, and the inequalities satisfy the normalization assumptions, and we have our f strictly positive on S, if C and L are the Logistic coefficient and exponent, then we know that F belongs to the level L of the truncated quadratic module. If look at only at the second line, if L is bigger or equal than a constant gamma that depends only on G and N times the degree of F to a constant times N times L times epsilon of F to the power minus 2.5 times N times L. So it is important. I want to remark that these exponents here are not the best ones given by the proof, especially for n much very big. This is not optimal. I would say that you can imagine that these exponents are roughly divided by 3 when n goes to infinity. And these are the real exponents that we get here. You should see them. This is the real bound that we have, but not so important. Okay. So going on, what are the important things? The first, if there is a polynomial convergence in epsilon of F, that the parameters involved, you can see in the first line, there is the number of variables, the number of inequalities are, the degree of the inequalities, the degree of F. These are known parameters, so the only, say, mysterious one are the Logistic constant and exponent. And these depend on the description of the same algebraic set. Okay, but at least for the exponent, we will prove that n is equal to 1 in regular cases. So you can fall asleep if you want when I explain briefly the idea of the proof. So we can write, the idea is the following. You write f as p plus q, where p, or f minus q.
There's a question. Lorenzo, can I ask a question?
Yes, sure.
So in the Niche-Weighofer's result, it depends on the degree is exponential of n power d.
Yes.
So do you also improve that?
Yeah, I mean, there is no exponential dependence. Oh, no, sorry, not here. There is no exponential dependence. There is a constant times n cubed 2 to the power this, and the degree appears here. Degree of f times to the power something.
So you have d power n instead of having exponential of n power d, right?
Sorry, you have, can you repeat?
You have d power n instead of exponential of n power d.
Yes, yes.
Okay, thank you.
Okay, so I can go on. Sorry, I was here. Okay, so we have our P. We want to construct such a P which is bigger or equal than f star over 2, let's say, on the hypercube. And we want the Q that we use to construct such a P to be in the quadratic module of the GIs. Why this concludes the proof? Well, we have that if we know that P is in the preordering of the hypercube by the result of Monique and Lucas. And this is easy to show that is inside the quadratic module defined by the ball, the unit ball. And so we have that f equal to p plus q is in our quadratic module, since we know that this ball is inside our quadratic module by the normalization assumption. And okay, you have to imagine that to make this effective, you have to consider the degree of all these representations to get the bounds that we have. Now, what is the problem? The problem is the construction of Q, and we have to bound also the norm of Q and the degree of Q in order to apply the result of Monique and Lucas. How do we construct such a Q? Is one of the main differences between our proof and Marcus' proof, or me and Marcus' proof. We construct Q in this way. We say that it is equal to a constant S times the sum of H of GI times GI, where H is a univariate polynomial echelon function. I will explain in the next slide the detail. Let me remark the difference. In the previous works, this coefficient was constructed as a univariate sum of square polynomial. And if you construct it in this way, it is immediate that you have something in the quadratic module, while with our new functions it's not so easy to prove, it's not clear. But you have worst bounds for the norm of Q and worst bounds for the degree of Q. While with these functions, it is easy to find these bounds. And let me show you how we construct this function. So look only at the picture at the beginning and look at the black function, which is a kind of indicator function. It is equal to 1 on the negative part. It is equal to, say, a small value on the positive part, and then there is a step here which is enough smooth, let's say. And what we do is we construct our H as a polynomial approximation of this echelon function. So we have our red function, which is a polynomial echelon function, and you see this is a uniform approximation of our black curve. So what we can prove once that we construct this red function, our coefficients, we can prove that H of GI times GI is in the quadratic module. And then we have to analyze the degree and the exponent of this function, HKM. So this will depend on delta, which is the width of the step that you have to make between the constant one function and the small part. And this delta depends on C, L, epsilon, and D, all the parameters. And so, and the same will hold for M, which is the degree of this function, K, which is the minimum value of this function, and S, which is the coefficient that I've shown you in the previous slide. This all depends on delta and on R, the number of inequalities. And okay, so what we do is to analyze these parameters. We deduce the order of this of the degree and of the norm, and then we conclude applying the result of Monique and Lucas. Okay, let's move to L equal to 1, the logistic exponent. If you look at this example that came out in a discussion with, yes, there is a question. Yes. How do you choose the black function in the black? You have, okay, the black function, it is constant to 1 on the left. Okay, then it is equal to 1 over k, where k is another parameter in 0, 1. So when k will go to infinity, so it will be closer and closer to 0 on the right part. And then you have to choose how small is this width, is this step, okay? And this depends on the Logistic exponent, on the Logistic coefficient, on epsilon, and on the degree. So the worse is the problem, the smaller will be this step. So it will be, the first derivative will be going to infinity, if, I don't know, if L is going to infinity, for instance. Okay. And then you compose it with the GI. Yeah, and then you say H of GI times GI. And what? No, this was already in the paper by Marcus and me, but they use another function. They use univariate sum of squares. So instead of having a function which looks like 1 something small, they had something like they could, I don't remember exactly, but there was something going to infinity. And this, because it was a, say it was a square polynomial. It was like, I don't know, 1 plus t to the power 2m, where m goes to infinity. So it was like growing. Okay. There are other questions? No? So I go on. So as I said, this example came out in a discussion with Adam Paruzinski. And so if you consider this univariate simple example, you have an interval included in -1, 1, defined by the natural description, epsilon square minus x squared. In this case, it's very easy to show that d of x is more or equal than 1 over 2 epsilon times the algebraic distance. And this follows, for instance, because the distance, if x is between epsilon and 1, it is x minus epsilon. And then g of x, it will be x plus epsilon and x minus epsilon, and then it's trivial. So this example shows that L is 1 in this regular case, this regular univariate case. And on the other hand, if epsilon is 0, so g of x is minus x squared, it is a singular equation, then the image of x set is just 1 point. The gradient of g vanished there. And in this case, you can prove that L is equal to 2. So this suggests something, and we generalize this. So we need this definition coming from optimization, the constraint qualification condition. So if we have a point x in this image of x set, the active constraints at x are the gi such that gi of x is equal to 0. And the constraint qualification condition holds at x if the active constraints have linearly independent gradients. And what we proved is that if the constraint qualification condition holds at every point of the same algebraic set, S, then the Logistic exponent is equal to 1. So the algebraic distance, it's linear, like the distance, somehow. And this has as immediate corollary an improvement of the previous results with the exponent that disappears, L equal to 1. Remember also that these coefficients, these exponents here are not really optimal, they could be improved. This could be, I think, like 0.8 n, if I'm correct, or even less, maybe. Okay. Maybe it's time if there are questions on this part before I move to other applications.
So how would the bound improve if you were on the box in the first place? So you didn't have to do this.
Well, the box in the first place, it is a Smoot-Gen result by Monique and Lucas, and it is, you can see. Well, you cannot have the Putinar for the, it's not immediate, it is, no, maybe, no, it is Archimedean, probably also.
Yeah, you present them as squares.
Yeah, you're right. We didn't try, to be honest. I don't know how it would be to prove Putinar in this way.
Well, let's say that you have a box and you add a ball around the box for your representation. Redundant one.
Excuse me, would you mind repeating the questions? Because we can't really hear.
Sorry. So my question was how much the rate would improve if they considered only a box. And it, of course, depends on the representation of the box. So let's say that the box was represented by quadratic polynomials for the GIs plus a ball constraint around the box.
And the answer is that we didn't try, and I don't know. I would say that as future work, we would like to prove this kind of example to improve the bound for specific examples where we can really give a number to this gamma, and also these exponents can be studied in a better way. Okay, I think I can go on. Okay, first application that I promised at the beginning, application to the left-hand hierarchies. You recall F star is our minimum, F star SOSL is our lower approximation. How good is our approximation? And this is our answer. The approximation is going polynomially in L, in the level, in the order L of the approximation that we are doing. And in the previous result by me and Spehofer, this was logarithmic only, because the convergence was exponential for Putinar. So we get only a logarithmic convergence for the Lasserre error. And also remember that this can be improved in regular cases, as I just shown. We have n equal to 1. In these cases, I've said common in polynomial optimization problems. Okay, I don't know how. Yes, I can go on, I guess. I want to also to describe another application that is to moment sequence convergence.
Wait, Lorenzo, can I ask again a question on this dependency in the number of variables and degree? So, okay, so it's polynomial convergence in L, but what about the dependency in N?
Oh, in N, it's not so good. This is, again, you are anticipating what we would like to do in the future. We would like to remove N from the exponent.
Because if you use niche Weinghofer, how is the dependency in N on the right-hand side here?
Niche Weinghofer is here, and I think that there is there is e to the n to the power d, which is very bad already. But I think also there is also an n hidden here in this c. I may be wrong. It is exponential in n here.
Okay. Because I think you also have some exponential or maybe doubly exponential dependency in n in the last formula you showed.
Doubly exponential,
But
I don't.
Maybe it's different. No, not here. If you look at the difference between the minimum and the bound.
Yes, sir.
So
There is no doubly exponential, I think. It is exponential in n. Yes, I agree.
but then you take the power 1 over n again. So. Okay, so it's not so bad. The gamma prime is not so bad.
Yeah, you have to look at the gamma second here.
Okay.
If I may shortly comment on this. So if you go back to a result of Chia Wang Ni and myself, in fact, what you said already is that C, there is a dependence on n hidden also in the C, in the constant C, right? And nevertheless, it makes sense to write this n to a d, because here the n and the d are appearing, the C doesn't depend on d. That's why I wrote nevertheless the n to the d. All that makes sense. And yeah, there is this dependence on n can be very, very bad because it's also hidden in C in our result. So I think that this new result is much better, actually. Thank you.
Thank you for the comment. And since we are in this direction, let me comment where this n is coming from. So since we are here, this n is this n. So we have that this constant in the theorem by Monique and Lucas depends on d to the power m. This d here will be m, essentially the degree of the polynomial echelon function that we have to construct. And this m will have a dependence on epsilon, let's say. And it will have a dependence, on epsilon to the power L. And then you compose it, and then you have epsilon to the power L times n. This is how you get this n. So of course, any improvement here would get an improvement in our result directly. Okay, so I think I can come back. I don't remember where I was. I think I was here. So and I was trying to arrive to the application to moment sequence convergence. Maybe I have time. Yes. Okay. I just briefly recall the notations that also Bernard used yesterday. So we identify a linear function of sigma, applying that acts on polynomials with the sequence of coefficients, or sorry, of moments, sigma alpha, that is sigma applies to the x to the power alpha. And we need also the notion of restriction of a linear function of sigma to polynomials of degree at most t, or in coordinates, if you prefer, sigma t are the moments of sigma alpha such that alpha has norm smaller or equal than t. Okay, and with a slight abuse of notation, we will consider Borel measures supported on S as linear functionals. So we identify measures with their moments somehow to simplify the notation. And okay, I described the ESR moment hierarchy here. And so we have L of G, that is the dual convex cone of the truncated quadratic module QL of G. And these are the linear functionals such that for every Q in the truncated quadratic module, sigma applied to Q is bigger or equal than 0. And then to try to define the hierarchy, we need to take an affine section of this. So we consider the linear functional such that sigma applied to 1 is equal to 1. And these are the feasible moment sequences, if you want to use another language. So for L natural number, we define F star MOML as the infimum of sigma applied to F such that sigma is a feasible moment sequence. And this gives a hierarchy of lower approximations to F star. And notice that the Borel probability measures on S are a subset of this feasible moment sequence. So the question is, if we have, okay, if we do know that there is convergence in value, but another question is, are the linear functions that we use close to measures? And if yes, what is the rate of convergence? Well, the answer is yes in the Archimedean case, as was shown by Marcus for polynomial optimization problems. And it is also, the answer is also yes, as Matteo Tacchi has recently proved, for the generalized moment problem under the hypothesis of bounded mass constraint, which mimic more or less the sigma of 1 equal to 1, let's say. Okay, and if you want to have some other rate of convergences for the simplex and the sphere, if I'm correct, there is a result by Phillips and Etienne about the rate of convergence of these lower approximations, also for the generalized moment problem. Okay, now what we want to prove here. We already know that there is convergence, but what we can prove is that this convergence of the feasible moment sequences to measures can be deduced. The rate of this convergence can be deduced from the effective Putinar's Positivstellensatz. I don't want to enter into the details of these bounds. They are horrible, of course. But what we can prove is that the convergence to moments of measures depends on the effective Putinar Positivstellensatz. It's a direct application, let's say. So some remarks. The first is that we focus on all the moment sequences, all the feasible moment sequences, while in the literature, usually what is proven is for optimal moment sequences, for minimizing moment sequences, but it is quite easy to prove that these two approaches are equivalent. It's just a matter of taking a constant objective function, let's say. And so, the third point, the rate of convergence is coming from the effective Putinar's Positivstellensatz. And we proved it for the polynomial optimization problems, but I think that our result could be easily extended to the generalized moment problem. So the idea of the proof. So we have that a linear function of sigma is coming from a measure if and only if it is non-negative on positive polynomials. And if you look at our positive linear function sigma, our feasible moment sequences, you know that we cannot prove that we have something non-negative, but we can prove that we have something bigger or equal than minus epsilon, let's say, for some epsilon. And this happens when you have a level L which is big enough. This level L is given from the effective Putinar Positivstellensatz. And now I just want to conclude with a picture, well, with a drawing, so to explain quickly what we did, which I think can be interesting. So you have here, you can consider the cone of Borel measures. And okay, what we have in polynomial optimization, we have our outer approximation. So we have L, let's say. What does it mean to say sigma 1 equal to 1 means simply to take an affine item. Okay, and what are the feasible moment sequences? It's here, right? These are the feasible moment sequences. Oh, sorry. And here in the middle, you will have probability measures. This is LL1. Now, how do we bound it? What I said is that sigma applied to F is bigger or equal than minus epsilon. What does it mean? It means that we are kind of considering a cone, which is, say, it's not a convex cone, it's a cone, it's a translated convex cone here. And we know that the feasible moment sequence is L1 will be inside this translated cone that is at distance epsilon. If L here is big enough, this will be inside this translated convex cone at distance epsilon. And so what we can prove first is that the distance between this and this is smaller or equal than epsilon. Now, this is not the end of the story, because here, the measure that we get here may be not a probability measure. We would like to be here, but then what we do is the following. We know that the moments, the feasible moments in the Archimedean case are inside a big ball of radius, I don't know, capital R. And with this bound, we can finally compute this distance. That is the distance that we are interested in. So this is the idea of the proof. And I can conclude, I think, if there are no more questions about this.
Lorenzo,
Yes.
Can you hear me? That's Didier Orient.
Yes.
Yes, I'm wondering, so you're considering distances in the infinite dimensional space of sequences, but...
No, I didn't write it.
So it's finite dimensional what you're doing? I missed that.
This is here. So 2t for some t dual.
Ah, for t, for the degree given.
So, I mean, we fix 2t, fixed.
Okay.
Fixed. So
Yes.
we have our moment sequences that goes from degree 0 to degree 2t. Okay, let's
Yes.
say. Then we have L. L can, say, this is for L equal to 2t. Then we
Yes,
have
this L is just the dual of the quadratic module, right?
It's more or less, sorry. So we have L, say for L, we start with L equal to t, then L equal to t plus 2. What happens? We have a longer sequence, right?
Yeah.
But this part we cancel. Then L equal to t plus 2, plus 4, 0, this, and then we cancel again, right? So
Yes.
we can compare all this. For every t, we can compare the degree t moments.
I see.
And we let the degree of the Lasseriarity go to infinity.
Sure.
So
And
we fix
so-
t and we let L go infinity.
And what is the dependence of your rate of convergence? What is the dependence on t? Where does it enter?
There is no depend. I don't remember. I know there is a dependence on t, but
It must be, otherwise, if it's uniform in t, it does not depend on the dimension.
no, it's t. It depends on t. Sorry, it's here.
Okay.
See, there is n plus t choose t to some power.
I see. Okay.
And also t, well, I mean.
And
here.
so, yeah, but if t increases, then the rate worsens significantly, right?
Yes.
Okay.
So if you want to consider, say, only degree 1 moments, you have a result. If you want to consider degree 10 moments, you will not
I
get
see.
it.
Okay. Thank you. Thank you. That clarifies. Thanks.
Can I ask again a question? So,
Yes, sure.
so how do you explain that the rate is worse than the one for the degree of Putinar's representations?
I explain it because in the Putinar representation, you are taking into account epsilon of f, so the minimum, okay? While here you are, say, moving, these are all the feasible moment sequences, not only the minimizing ones. You have to take to consider the worst case scenario. This is what I have in mind.
Okay. Okay.
So I mean, okay, this is not, maybe it's not a good picture. If this slice now becomes a plane, right? You have, I don't know, here the measures, and you have your outer approximation. I want a black here. Okay, this is the outer approximation, L1, right? And when you optimize something, you may be optimizing this, that gives this one, but you may be also optimizing this one, right?
Yeah.
And so the quality really depends on, we are bounding the worst case,
Because if you assume that you have a ball constraint, then the bounds, they are equal, right? The moment bound and the SOS bound, they are equal. So,
no,
but indeed, the feasible optimization set is
okay. I have to be precise about this. This bound is not on the value.
Yeah, sure.
It is on the distance between the moment sequences representing measures and the moment sequences that are not representing measures.
Yeah. Okay. Thank you.
You have to. There are two different. There is the convergence in value, which is the one. I mean, this convergence, of course, is valid also for the moment relaxation. If we are in the Archimedean case, and so this is, let's say, equal to the moment one when you add the ball constraint by the result by strong duality, or the result of Didier and Jost. So you don't have any duality gap here in value, but these results is the distance between moment sequences. So it is telling you how good is your auto approximation of measure, not really how good is the lower approximation of the minimum that you find.
So it's a worst case situation. For the worst possible linear functional, you get that, right?
I would say yes. Bernard wants to say something? No?
Yeah. So the bonds are worse because you have this T, which appear. Otherwise, it's about the same order. But the T and this quantity, which depends on T, is in fact related to the dimension of the polynomials of degree less than T. And this constant appear because we have to compare. We have to do this projection.
Yeah, we may think of an analysis which would not depend on T, provided you have the correct topology on infinite dimensional moment sequences. But here, definitely, the dependence on T is strong. Yes.
I think it's very difficult to go if you move to the infinite dimensional setting to describe the distance. I mean, the distance in the Archimedean case, if you are in the infinite dimensional setting, is 0, because all the elements in the dual of the quadratic module are measured. In the full dual of the quadratic module, it's the where is it? No, sorry, here. I mean,
Yes, but you are interested in truncated quadratic modules and their duals.
yes, but this holds, right?
Yes.
So if you truncate, then the same holds. The problem is when you put something here. When you are not considering the dual of the full Q, but you are considering this object. When you are considering only the truncated quadratic module and you are taking the dual of only of the truncated part, which is very different from taking the dual of the quadratic module intersected with polynomials of small degree.
Yes, but here you see you have two indices. You have L, which
Yes,
is a relaxation order, and
yes.
T, which is a truncation order. It's so you can still study what you're doing, but for T infinity, and you would look only at the rate of convergence in terms of L.
No.
No.
What sorry.
So T would tend to infinity, but L increases. The relaxation order. You want to know how good you approximate the whole moment set as a function of L, the relaxation order.
Yeah, you would like to do it, but it is not really possible because if you look at the moments, concrete moments coming from examples, for instance, you see that the highest order moments are always very bad.
Okay.
Because if you don't discard the highest orders, there will be a kind of perturbation that you're not avoiding. The relativity conditions is not strong enough to correct the highest orders.
I see. Yeah. Okay. Good
So
point.
I mean, maybe I can also do an example.
Yeah. Good point. Good point. Yeah.
You will see that, I don't know, you want to obtain the evaluation at 0, so you want to obtain 1, 0, 0, 0, and so on. And then what you will see is 0.99, 0.99, then 0, 0, 0, and then 240. It's really the highest order terms are not good. You have to discard something.
Makes sense, yes. Yeah, thank you.
Can I ask a question?
Yes.
So thanks, Lorenzo, for the nice talk. I would have two small questions. So on the way you use our result on the hypercube. So the first question would be, if suppose there would be, so the result now is using the preordering.
Yes.
And suppose one could get a result for the quadratic module of the box.
Yes.
Does that help you?
Not really.
Because on the other hand, you could replace the hypercube by the ball.
I can show you why it doesn't matter. Where is it? It's here. So the preordering of the hypercube, you see, it's inside the quadratic module here.
Okay. Yeah.
And so this is the degree D preordering, the level D, and this is level D plus N. So essentially, in order to have this inclusion, the only thing that changes is plus N. If you have the quadratic module here instead of the preordering, you just say one N here, but this is not really, it doesn't change the asymptotic behavior.
Okay, thanks, that's clear. And maybe a second question. So you now used the fact that this constant C and D is polynomial, so I hope I say it well, is polynomial in N for fixed D.
Yes.
Yeah. And so with another version where one can also say that this constant is polynomial okay.
There is a version that is polynomial for fixed N. It is for fixed D it is polynomial in N. Okay.
Yeah.
But then this would not be good for us because for fixed N, So if you if you put D in the exponent, essentially, you can do it. But the D here will be the D here is this M. Okay, the M is the degree of this function. And the degree of this function is like epsilon of f.
Okay.
So you would get an exponential bound because you put the epsilon on the exponent.
Oh, okay. Okay, so the degree becomes, okay, I understand, yes. So it doesn't help you at all, this second one.
No.
Okay, okay, okay. Thanks a lot.
Any other questions for Lorenzo? But maybe you didn't finish, right?
Yeah, sorry. So
This correct. Yeah.
maybe I can finish that. So the take-home message is the first, that effective Putinar Positivstellensatz has a polynomial rate of convergence on epsilon of f. And this gives a convergence rate of the Lasserre hierarchy that is also polynomial on epsilon of f. And also the convergence of feasible moment sequences in polynomial optimization to measures. And now let me repeat again all this perspective that you already mentioned. So first is the effective Putinar Positivstellensatz in specific examples, as was asked by the audience before. And then the second question could be, okay, we have seen that for a regular problem, we have L equal to 1, but we didn't prove that for a bad problem, the exponent is bad. What is the converse of this implication? And we say that if L is big, then the dependence will be bad. It would be nice to know. And the third question, already mentioned again, is that can we improve the exponents, and especially can we remove L from the exponents? This would be very nice. So we would like to have a result that is similar in the spirit to one of Monique and Lucas without N in the exponents. And the third possibility could be to compute the rate of convergence for moment sequences in the generalized moment problem. So here you can find the reference for the preprint, and thank you for the questions and for your attention.
Okay, many thanks, Lorenzo. Very exciting result. So are there any more questions for Lorenzo?
Yes, it's Didier again. Maybe just a suggestion for the terminology for this study on the moment convergence. So you're using this curly L, which is a dual to the quadratic module. So this is the what some people call pseudo moments. They are not necessarily moment of measures.
Yes.
So,
I mean, this is why I always put the linear functional with its sequence of moments.
Yeah, so it's when you say moment of relaxations converging to measures, I would rather say pseudo moments convergence to genuine moments. I think
Yes, okay.
this covers better geometrically what you're doing, but that's just a suggestion. And I guess, and then I have a side question, but I guess you also get the same result in to approximate positive polynomial by sum of squares from the inside, right?
Yes, I didn't present it, but
that should follow immediately, no?
Yeah, it is this Weierstrass, uniform Weierstrass theorem. I don't remember where is it. Maybe it's here. Yes, this one. I cannot. I would like to zoom results less, but it's not. I cannot find it. Because this one. Okay. So you see, blah, blah. We have an effective version of what? You have that f minus f star plus epsilon belongs to the truncated quadratic module. This is what we were saying. If we have a function f, which is
yes,
this is more or less what you were saying. It follows immediately.
Yes. Yes. Yeah. Okay. Very nice. Thanks for the very interesting talk.
Yes. Let me also answer a bit your first thing that we shouldn't call moments what is not a measure, but indeed, if you assume that you have these positive semi-definite matrices, moment matrices,
Yes.
even if you don't have measures, you inherit, say, almost all the properties of the measures. And so this is, I mean, it's
yes,
not all the measures, of course, not all the properties, but many things that you can say about the kernel.
Sure, but it's mostly a terminology issue in the sense that in this curly L, small l of G cone, which is dual to the logistic module, there are elements which do not come from a measure.
Yes, exactly.
That's it. So we may call them pseudo moments. Or, so it's not really feasible moment sequences, as you're right, because they are not necessarily moment sequences.
Yes, feasible pseudo moment sequences.
Pseudo moments in the sense that they are not necessarily moments, and what you're studying is how fast they converge to genuine moments. Of measures.
Yeah, this is absolutely what we do, and simply prefer to use the word moments, even if it can be confusing for these sigma alpha. Sigma is the measure.
It's true that we use also the terminology moment matrix for just the matrix itself, and if it's positive semi-definite, it does not imply that its entries are moments, but its structure is that of a moment matrix. So indeed, there is a little confusion in the terminology. I agree.
Can I say something about that?
So any other questions?
May I say something about your comment, Didier? So moments here are used in a very general way. So there are moments which appear in different contexts.
Well, in a general way, but in general, in which sense?
Well, different contexts, so not necessarily directly connected to measures. For you, moments are moments of measure.
Okay, you mean linear functionals then, just?
And coefficients, yeah.
Coefficients of linear functionals, yeah. But that's not necessarily what people call moments, at least in the papers I'm reading.
Yes.
There could be maybe coefficients of distributions in the sense of charts, but not necessarily moments.
Okay, any maybe last question for Lorenzo? Okay, so if not, I would like to thank you again, Lorenzo, for this very nice talk, and all the speakers of today's session. So we resume tomorrow at 9:30 with Corby, who is going to talk about sparsity. So meanwhile, have a good end of afternoon, and see you soon.